In this video, we will learn an important compression algorithms called Huffman coding. We will start with a simple example and then we will answer a key question that when Huffman coding is optimal. Some people think incorrectly that Huffman coding is always optimal, but this is not correct. So we will discuss specific scenario where Huffman coding is optimal. We will also compute its performance by calculating efficiency and redundancy. So let's start with an example. We are given some symbols and their corresponding probabilities of occurring in our data. We put all those symbols and their probabilities in a min heap. So here I have a min heap. In the start, the min heap have all the symbols and corresponding probabilities. I'm not creating min heap, but I'm just adding nodes in a min heap. So min heap will have this node, it will have B with value 2 over 11, it will have node C with value 1 over 11, node B with value 3 over 11, E with value 4 over 11. We can make a Huffman tree to visualize that how our algorithm works. So in the tree, we will first make leaf nodes. And in the leaf nodes, we will put all the symbols and their corresponding probability in a sorted manner. This is just a visualization. We don't actually have to create Huffman tree in the memory when we are implementing Huffman algorithm. So here I have a leaf node A with probability 1 over 11. I'm sorting all those nodes with respect to their probabilities. Then I will have C because it has the second smallest probability. Then I will have B with probability 2 over 11. I will have D with probability 3 over 11. And finally, I will have E with probability 4 over 11. Now, here we will use min heap and we will extract two nodes with the least probability out of the min heap. So, these two nodes will be extracted from the min heap and we will combine these two nodes to create a new node. So, we create a new node. Let's call this node AC with value 1 over 11 plus 1 over 11. So it will have a value of 2 over 11. And we will insert this new node in our min heap. So now the min heap has AC with value 2 over 11. Now the left edge of this new node will be labeled 0 and the right edge will be labeled 1. And that's it. We have to continue this process again and again until we have only one node left. So now we have 4 nodes in our min heap. We will once again extract 2 nodes with the least probability. In this case, we have these 2 nodes with the least probability. So we will extract them. So A and B will be extracted. AC and B will be extracted. And we will combine them to create a new node. Let's call it A, B, C with value 2 over 11 plus 2 over 11 is equals to 4 over 11. And we will insert this new node in our min heap. So now min heap will have ABC is equals to 4 over 11. and we will once again label the left edge with 0 and the right edge with 1. We will continue our process. Once again, our min heap has 3 nodes. We will extract 2 nodes. So we will extract, in this case, D, and we can extract either of E or ABC. Both are fine because both have same probability of 4/11. So let's extract ABC and D, and we will make a new node. Let's call it ABCD, and the value of this new node will be 4/11 plus 3/11 is equals to 7/11. Once again, this edge will be labeled 0, this edge will be labeled 1, and we will insert this new node ABCD in our min heap. ABCD is equals to 7/11. Now we have to extract 2 nodes from our min heap, and this is an indication that we are at the end of our algorithm because we have only 2 nodes left in our min heap. So we will extract these 2 nodes from our min heap and create the root of our tree. So here these 2 nodes are extracted and we have our root node, and root node will always have probability of 1 in it because sum of all the probabilities must be equals to 1. So let's write here 1 and label this edge as 0 and this edge as 1. So now we are done with our Huffman tree. Let's call this tree as Huffman tree. Huffman tree. And we are ready to write codes for each symbol. So let's make a new column here and write here code. So code for symbol A will be the path that it takes from the root to the leaf A, and code for symbol A will be 0, 0, 0, 0. So 4 zeros. 0, 0, 0. We are done with A. Now code for symbol B will be 0, 0, 1. Will be 0, 0, 1. Code for symbol C will be 0, 0, 0, 1. 0, 0, 0, 1. Code for symbol D will be 0 and 1. 0, 1. Code for symbol E will be 1. We are far from done, although we have found a code word corresponding to each symbol, but we have to learn how to encode and decode using these code words, and then our example will be complete. And then we also have to find out that in what circumstances Huffman coding is optimal. So let's start. This is our example compress file composed of these binary digits, and we have to decompress it. Now please look at this Huffman tree. This Huffman tree has all the symbols on the leaf nodes, and this has a significance because no code word can be a prefix of another code word. For example, 1 cannot be a prefix of another code word. In other words, any other code word cannot start with 1. So you can see that no code word starts from 1. Similarly, no code word can start from 0, 1 except this one. So there is no 0, 1 here. Similarly, no code word can start from 0, 0, 1. Although here is 0, 0, 1, but not at the beginning. So no code word can start from 0, 0, 1. and this is called prefix coding. The advantage of prefix coding is that when we are scanning our compressed file from left to right, as soon as we find a code word, we can immediately replace it with the symbol. So we don't have to look ahead. So 1 is a valid code word, therefore we will immediately replace 1 with E. 0 is not a valid code word, so we will look at 0, 0. Maybe 0, 0 is a valid code word, and 0, 0 is also not a valid code word, so we look at 0, 0, 1, and 0, 0, 1 is the first valid code word. Therefore, we don't have to look ahead, we will stop here, and 0, 0, 1 is immediately decoded with B. Similarly, 0, 1 is decoded with D. We don't have to look ahead. As soon as we encounter a code word, we decode it. 0, 1 is D, and I think 1, 0 is missing here, and 0, 0, 0, 1 is E. So now we are able to decode a file that is compressed using Huffman coding, and we are ready to answer this important question, that in what scenario Huffman coding is optimal. So Huffman coding is optimal only in prefix coding. So there are a set of data compression algorithms in prefix coding. Huffman coding is an optimal compression algorithm among those algorithms. So it is optimal in prefix coding. For example, Shannon coding is another example of prefix coding, but that is not optimal. Huffman coding is optimal. Similarly, Shannon-Fano coding is another example of prefix coding, but that is not optimal. Huffman coding is optimal. Secondly, Huffman coding is optimal if our data is of specific kind. Our data should have IID distribution. So our data should have IID distribution. That means that each data element has identical distribution. So first I is for identical. For example, if this symbol is drawn from a distribution which is normal and it has a specific mean, a specific standard deviation, then this symbol must also be drawn from the same distribution. So all the symbols are drawn from the same distribution or from identical distribution. Secondly, each random variable, that means each random variable must be independent. What we meant by this, that for example, we can say that probability of E occurring, given that B is already occurred, must be equals to probability of E, and it must be equals to probability of E. That means this condition will not make any difference. That means in case of independent distribution, we can say that probability of maybe A or B will be equals to probability of A and probability of B. We don't have to use conditional probability here because A and B are independent random variables. So that's it. Huffman coding is optimal when we have these two conditions. Otherwise, it is not optimal. So far, we don't know any compression algorithm that is optimal in general for any kind of data. Next, we have to find its efficiency, and we have to find our algorithm redundancy. We know that the formula of finding efficiency is equals to entropy, which we usually represented with H, divided by average length of symbol. So that means average length per symbol. I have already explained in a video that what is the formula of entropy and what is average length, so I'm not going to repeat it here. In this case, my efficiency is 97.1%, which is quite good. Then redundancy is equals to average length minus entropy, and in this case our redundancy is I think 0.06, which is quite low. So for this example, Huffman has worked beautifully, but in some other scenarios this efficiency might be as low as 50 or 40%. But don't worry, we have many more interesting algorithms to study and learn together. So see you in the next video. Bye.